Okay, so we have covered the modal analysis of undamped systems. The idea being we find the modes of the system and the natural frequencies and convert the system to its modal coordinates, which is the modal coordinates are uncoupled so that we can solve the problem rather easily. And this is that happens for the undamped systems very nicely. That is the modal matrix formed out of the mode shapes of the system uncouples the equations. Whereas for the damped systems, it is not that easy. It is not that trivial. And I'll try to cover that part now. So we will have a viscously damped system in general. That is a system that has damping in it. Like there is, the system has n degrees of freedom, let's say. And we say that the damping force is expressed in terms of the damping matrix. And the idea is we want to use modal analysis here. If possible, we want to just use the modal analysis as we have done in the case of undamped systems. But we encounter a problem. That is, for a general case of an arbitrary C matrix, that is, if you form the equations and find out the results, we cannot uncouple the modal equations if C is not of a special form. If C is a general C matrix, well, it's really not possible to uncouple the equations. So you have to do something else. You have to convert the equations of the system to some kind of state space form in which you have first degree equations and then find the mode shapes, etc. But then you encounter the problem of having mode shapes that are not real, that is imaginary mode shapes, which are not easy to interpret physically. Physical mode shapes that we encounter that we have in undamped systems are nice and easily understandable. Okay, so we want to uncouple the modal equations, and we can uncouple those equations only in a special case, which is called the proportional damping case. Okay. And I'll try to show that to you when we can uncouple the equations. When can we uncouple the equations and when we cannot? Well, let's start the analysis. First of all, we start the analysis by first solving the eigenvalue problem of the undamped system. That is, we assume that the C matrix doesn't exist at all. You just cross it out, and you solve the, the undamped eigenvalue problem of the undamped system. Sorry, which is something like, k minus omega squared m u equals 0, and just this part is just a scribble. This gives you the natural frequencies and omega I squared and ui for I equals 1 to n. And then you normalize the mode shapes and get the regular, your P matrix, the modal matrix. Okay, that is what we do for an undamped system, but we have damping in the system. So what do we do? As you remember, we get, after getting the P matrix, we want to obtain the equation of motion in the modal coordinates, and to do that, we, well, we convert our equations into modal coordinates. You know, x is equal to pq, and x double dot is equal to pq double dot, so it's here. And then we multiply it by p transpose, we get this triple product. We know that this p transpose and p is identity. It is uncoupled. This is uncoupled. This is a diagonal matrix. P transpose kp is lambda, which is diagonal of the natural frequency squared. But what about this one? P transpose cp. Well, the problem is usually if you just select an arbitrary c, that won't be diagonal, and that is the problem. Well, if you don't get it diagonal, then you cannot uncouple the so-called modal equations. Not in the case of if you use undamped modes, that is, of the system. So the equations of motion of the in modal coordinates become uncoupled if this is a diagonal matrix. P transpose Cp is a diagonal matrix only. If this happens, then the equations get uncoupled because each of the equations will be separate. And the condition for that is quite simple. If you can uncouple the M equation, if you can uncouple a system with M, if you can uncouple a system with K, then if C is a linear combination of M and K, then you should be able to uncouple the C matrix using the C matrix as well. And this condition is called the proportional damping. That is, if C can be written in this form, then you have proportional damping and your equations can be uncoupled. If not, your damping matrix is non-proportional, and that is, well, that's not really uncoupled. You cannot really uncouple the equations. You have to do something else, and we won't be covering that in this course, okay? We will just look at the proportional damping. Now, proportional damping is something we use not because it is physically common, but rather it is mathematically very convenient. Okay, if you have proportional damping, you can just assume that, well, you can uncouple the equations and then solve for them. And therefore, even if it doesn't reflect reality, we use it because of its mathematical convenience. Okay, because it's quite convenient. So, if C is a linear combination of alpha and beta, then P transpose P can be written as P transpose times alpha m plus beta k times P. So P transpose MP is an identity matrix. P transpose KP is lambda. Alpha and beta are simply coefficients, scalar coefficients. So they don't change anything. So you have a diagonal C matrix now. So the P transpose CP will be equal to alpha I plus beta lambda if this is satisfied. Okay. In that case, our equations will be diagonal. That is, modal equations will be diagonal. That is, they will be uncoupled. And you can write them as Qi double dot plus 2 zeta omega I Qi plus omega I squared Qi is equal to capital Qi. This is, as you might remember, the equation of motion for a damped second order, well, first 1 degree of freedom system. And we have n of these, and these are solvable. That is easily solvable. And here we have defined a 2 zeta omega I as alpha plus beta omega squared, just from here, as you might remember, omega I squared, so that we have defined a modal damping ratio. The damping ratio for the ith mode can be obtained as a function of alpha, beta, and omega. If you somehow select alpha and beta and omega, well, alpha and beta rather, omega is given, you can get any kind of a modal damping ratio, or alternatively, you can select a modal damping ratio, and from there you can get an alpha and beta. It doesn't matter. But then you can solve for your system's equations. I have given a terrible looking solution here, but it's not that complicated. This is the response to the initial condition Qi, this part. This part is the response to the initial condition Qi 0, okay? And this is the response to capital Qi, which is the generalized force with respect to the ith generalized coordinate or ith modal coordinate. So you can, this is the very general solution from which you can obtain the physical solution by back transforming to the physical system. Okay, this is possible to do. You can do this if your system is proportionally damped. If not, well, then you have to convert the equations to another form. But we are not going to cover that. What you usually do is the following. You just ignore the physical situation and assume a modal damping ratio. And from that modal damping ratio, obtain a C matrix from, you don't even obtain a C matrix. You just write the modal equations like this, solve them, and then obtain the physically damped solution. Okay, the damping will be eventually the system will the damping is going to die out. By the way, another thing is that the solution I have written here is for the case of an underdamped system. Okay, so that this solution contains sines and cosines. If zeta I is greater than 1, then you have to have exponential decays without oscillations. Anyway, such is the case for the damping, proportional damping. The modal analysis can be extended to the case of proportional damping. So I will give you an example which I have taken from the book by Kelly. Actually, there are so many equations there that I didn't want to copy them. I just, copied the picture here. So you have a system with 3 masses, 4 springs and dampers. And for some reason, the mass is 2 kilograms, the C is 17, and K is 200. And as you see, since the structure is very symmetric, you have 2K, 2C, KC, 2K, 2C, etc. This can be represented by proportional damping. The equation of motion can be written as follows. The damping matrix is proportional to the stiffness matrix, so you can write C is equal to alpha times K. And the proportionality constant can be found from C over K. So these two matrices are proportional to each other. You don't even have to use the mass matrix. The natural frequencies can be found from solving the regular eigenvalue problem. Okay. This was solved in another problem. It doesn't matter here. The natural frequencies are as follows. And the modal damping ratios for this system is zeta 1, zeta 2, zeta 3 is, alpha omega 1 over 2, alpha omega 2 over 2, etc. It is 0.38 is the first damping ratio, 0.9 is the second one, and 1.10 is the third one. Note that the third mode is overdamped. Okay. And the modal equations, well, I have been using Q's, but this book uses P's, so just P are the modal coordinates, okay? So the modal coordinates are, in the modal coordinates, the equations are uncoupled, and there you have three of them. And by the way, the initial condition was that it was 0, 0, and you were to pull this thing, the third mass, an amount of delta, and that's what we want to find. The solutions of these equations in the principal or the modal coordinates is as follows. You can find them rather easily. Here you have A1, A2, A3, phi1, phi2, and A4. You have 6 constants to be determined. And P3 is, as you see, is 2 exponential decays because this is an overdamped system. So you apply the initial conditions. It's just it's a procedural thing. If you apply the following initial condition and that the damping coefficients are zeros, all of them are zeros, you can find the solutions in the modal coordinates. Okay, these are the solutions in the modal coordinates for a delta of, if you pull this third mass amount of delta. And then the generalized coordinates are related to the principal or the modal coordinates by x equals p times p, which we call it p times q. So if you multiply this is your p matrix times your p terms, which is here, these ones. If you multiply them, you get the following complicated looking solution for x1, x2, and x3, in which the response eventually goes to 0 and dies out. You can plot this using a software or something. Okay.